So welcome everyone. This is the sixth lecture of the mathematics and statistics of infectious disease outbreaks. And today we will be talking about latencies and delays. There will be two topics today. The first will be, we will talk about back calculation. So trying to infer time of infection from time of symptom onset. And we will use a case study from a foodborne disease outbreak. And then we will continue looking at nowcasting or reporting delay adjustments for the same outbreak. We'll do these in two videos. The first will be the back calculation method, and then part B will be the nowcasting. So as a motivating example, there was a very large outbreak of foodborne disease, Escherichia coli, a particular type O104H4. So there are many different types of E. coli, but this one was a particular subtype, and it induces diarrhea typically. And what is one thing which is special about this type here is that these Escherichia coli infections can lead to an additional complication, which is called the hemolytic uremic syndrome, HUS. And it's a disease which is characterized by loss of white blood cells and acute kidney failure, and can ultimately lead to death. So this outbreak was in particular a bit special. It occurred during May-July 2011 in Germany, mainly in Germany. And usually the HUS complication is something you rarely see in adult. This is something which you usually, if then, observe in children, but here it was actually a huge number of adults which were infected, and totally there were about 50 deaths from the total outbreak. And what is sort of like astonishing is that these were more or less rather young of age. And there was a proportion, the proportion of females which got infected by the disease was higher than for males. And so you see case fatality ratios of 0.6, 4.1 for the HUS, and it ultimately could be proved that it was associated with the consumption of sprouts, and which could explain in part due to eating habits that why the females were harder affected than the males from all of this. It caused a lot of attention, at least in Germany, but I think even in Sweden, a number of travelers who went to Germany were affected by the disease. So maybe some of you remember this outbreak. And what is interesting is, of course, here is that HUS occurs about 5 days after the onset of symptoms. So that would be typically the diarrhea of the STEC, which also takes about 5-6 days to happen after you got exposed by the disease. So what is important to know about this disease, it's mainly foodborne. So it's a bit different than these person-to-person transmitted diseases that we've looked at so far. So here it's a contaminated product which you need to eat, consume, and then you usually get the problem. There's a small fraction of person-to-person, usually so you get in contact with the stool of people in some way. So there could be bad hand hygiene, for example, or you share the same toilet and the same towels or something like that, which could be one way that there's a person-to-person transmission here. But to be precise, this was a minor part of the outbreak, was the person-to-person. The major part was sort of like find what is the culprit. And here in this case, it took a while, but then ultimately we could say it was sprouts. So there's also a branch of infectious disease epidemiology, which is very much disease detective work, trying to figure out why are people getting sick, what is the disease they're getting sick of. And the other thing is sort of like, if it's a contaminated food product, foodborne diseases, try to identify the food product and get it out of the store so no more people get infected. And of course, then you want to sort of like, where did it come from? And how can you change routines so this is not going to happen again? So this is about also trying to make sure that these products don't even enter the country if it comes from abroad, or that they change hygiene in the production facilities, as an example. So this is something, I mean, this is just one outbreak of many, but it was because it was an unusual disease in that sense that it was HUS among males. It caught more attention than a typically foodborne outbreak. But there are many foodborne outbreaks always ongoing, salmonella, but it's not as fatal as this one here. So this could be the reason that you don't hear a lot about sort of salmonella outbreaks, norovirus outbreak due to contaminated food products, but they occur in Sweden all the time. I think you can read the reports also by Folkhälsomyndigheten, and you would see that you have a large number of cases from something like that as well. But we will use that as a motivating example. So here's the epidemic curve, which you already now know. So we show after the outbreak occurred, when it's done, we show the number of reported cases of diarrhea confirmed. So that would be the top line. So that would be either, so they had at least STEC, and maybe including, but maybe not including the HUS, the proportion of individuals who had HUS with reported symptom onset of the diarrhea is the blue curve, right? So these, you see that there's a certain fraction which got infected. So, but what we show here is the day of disease onset. So the diarrhea, initial diarrhea, and then the HUS comes a bit later as well. So you see here you have an increase and then a decrease. But again, remember, this is a foodborne outbreak. So there is a window of opportunity where it was possible to consume the food product. And then the question is the food product gone? And that's why it goes down. And it's just a long latency period of that people maybe have it in the fridge, or it takes a while to eat, or it takes a while to develop the disease. That's one question which is interesting. But don't try to model such an outbreak with an SIR model, because that's simply the wrong model, because there's little to none person-to-person transmission here. So again, you have to know a bit about the underlying disease mechanics in order to make appropriate modeling. So if you compare this curve here with some time points, and now here it's again important to be careful about. So we have here the calendar time. For example, here this was when the German Volksmündigheten for the first time was informed about what's going. That we have three HUS cases in Hamburg, and I think they were adults, so this is why they got alerted. That's the first time you hear about this at the Public Health Institute. And then there was a warning against consuming tomatoes, cucumbers, and lettuce in northern Germany. So that was about here where this was communicated. And you could think that, okay, this led to the curve dropping, and at that point here, the sprouts were communicated as source, and they were then here confirmed, and then this outbreak was more or less over, because one would identify the facility where it came from. It was closed, temporarily sanitized, and so on. And there was actually also even a backtracking of these sprouts, where they came from, and ultimately they proved to be from a batch from Egypt. But one never really understood why this was a particular bad batch. There was a concurrent small outbreak in France at the same time, but I'm not sure it has been fully understood why exactly this batch was the problem. So again, but please note that this is how you would see the situation afterwards, given that you see all the data, and this is symptom onset. So please, what is important is, of course, when did those people eat the sprouts which made them sick? So this curve more or less has to be moved a bit to the left in order to really understand that part, when they were exposed to all of this. So if you want to assess an intervention, for example, and that's what we will be looking at today, how to do such a back computation step. Maybe it's important to say, well, that's how it's always easy to be smart in hindsight, because I showed you how the graph looks now several years after the outbreak. I mean, you could do this graph at the end of the outbreak. So maybe in July, August, it was possible to draw the graph. But I mean, what is important to understand is, if you are, for example, a public health specialist, or you're a politician who has to make decisions about something like that, is that the data are not as clear as they look afterwards, right? So there's the incubation period, so from exposure to that the people get the symptoms, and also reporting delay. So from people who have symptoms to this case actually appears in your public health central database, that takes a number of days. And of course, these data then you haven't seen. So you don't know, you're really steering blindfoldly when you say, okay, what do we need to do? Do we need to put new interventions into place, or what should we do? It's simply not clear because you don't have the data. It takes a while before you actually see the data about the times where you made the intervention. So just to illustrate that here, I've shown day of hospitalization in HUS cases, because HUS is has such strong symptoms that you're almost certain to spot every case because they're very specific for HUS with the kidney failure and so on. So here's no question about asymptomatic cases and people not have gone to the doctor. So the STAC are a bit more problematic because if it's just diarrhea, not everyone goes to the doctor or gets a lab confirmation of this. But the HUS is clear. If you have that, you will go to the hospital or you will be brought to the hospital at some point in time. So these you won't be missing. And it's a day of hospitalization. That also means that the public health authority, at least at the local level at the hospital, someone in the health system knows about this case. And I'll show you the graph for this. So hang on, we have to change the share. So I will go web animation. Sharing is portion. I have to move to this one. Hang on. So web animation. Now we're sharing. All right. So you see here we have the curve as it looks at the end of the outbreak. And this is a bit sad because I wanted to have it at the beginning. Hang on. I have to figure out how I'll do that. I'll do pause share. I have to go back like this. I want it to go to the first time point. I'm pretty sure you cannot see this at what I'm doing now. All right. And then I resume share like this. So you should be able to see here's the time point. This is now. This is how the curve looks at time now is what you will be with shaded. You cannot see any of them because all cases are in the past, or there are no cases in the past. And this is how the truth materializes after the outbreak, right? So this is the light bars are, this is the truth, but you don't know that at the time of the outbreak. So as I said, 1st of May, so the first hospitalization in a case was here on 7th of May, but of course, as I said, the 19th of May was the first time that the Robert Koch Institute heard something about that. But in the official reporting database, so this was a telephone call as far as I've understood it, in the official recorded database, there were actually only one case. So not really a big outbreak, but this was already in the hospitals at this time point, but you just don't know about it because it's not in your reporting database. They might know it at the local authority, or they might know it in the hospital, because they have been hospitalized, but it's simply not transmitted the case yet on 19th of May. So and then you see sort of like, okay, that's when you start to realize you have a problem. And on 23rd of May, it was communicated, speed up the transmission of cases, no quality control, simply make sure to transmit the case as soon as possible. You can only withdraw it later if the lab is missing, or if it shows that it's another type of kidney problem and so on. So this is when they said, okay, speed up the transmission, no quality check and so on. And that's when you see sort of things start to happen. You get more and more cases. This is what you have in your reporting database. And this is what sort of really is the truth. I mean, what's amazing about this is, you see, this always looks, what you see in your data always looks like it's going down. So you always think, oh, this outbreak is over, no problem. But you can say in hindsight, actually, this outbreak was still growing. At this time, at least at this time point here, it was still growing, but you didn't know that. You cannot know that because you don't see the data. And okay, so always at some point it's going down, and now you of course worried is this downgoing trend? Is this an artifact? Because actually it's increasing, and this is just cases which have not been transmitted yet. But now in hindsight, you could say, okay, well, this was on the way down already, right? So just to say, things are not as easy if you are during an outbreak, and let's say you're here at 25th of May, for example, here you have to make a decision. Do you give a particular warning about consuming tomato, cucumbers, salad, or something which is associated with those in northern Germany? Do you give a warning or don't you give a warning? What should be the intervention measures, or what warnings do you want to give at this point? That's hard to really decide on when you don't have the full picture. But you have to be aware that that's how the data, I mean, you can speed up some of this, but that's often a data situation which you're going to have if you have to really make real-time decision making. Okay, so let's go back to the slides. Here, all right. And then I need to go to the slides. I think like this, and then we can make them full screen again. Okay. So these time lags, there are two which we will consider in particular. The one is the delay between exposure to disease and onset of diarrhea here in the cases. So that will be what we will call the incubation time period. And then there's the inherent reporting delay present in any public health surveillance system. It can be smaller or larger, which is the delay from here we will say it's the symptom onset until you have the report, but it could be from hospitalization until you have the report in order to take out that. It is a bit difficult sometimes to say when will people go to the hospital. It depends very much on how strong are the symptoms and so on. So there's a bit of individual variation there, but once they're in a hospital, for sure, the health system knows about it and should be fast in order to make interventions possible, or to get a full picture of the situation. So the first, the so-called back projection deals with this. Is once you see the onset of diarrhea in cases, how do you can actually compute back to the time where they got exposed to the disease or infected by the disease. And the nowcasting is dealing with the second part, is trying to make the current and available counts, try to extract reporting delays and adjust for reporting delays in order to get a full picture of what is your current situation. So for now, we will talk about the back calculation method. So what is back propagation or back projection? There is a method to adjust for the delay difference between the incubation time, and this is the incubation time, is the time between infection to the disease, or time of infection, and the onset of symptoms of the disease. It's not when you start to turn infection, but onset of the disease. In that you see symptoms, or that's an observable event, that the first time you really realize that somebody has this disease. And here, this is easy because we're assuming everybody will have symptoms. For COVID, this is, for example, a bit more difficult. What do you do about people who are not just pre-symptomatic, so it just takes a while before they get the symptom, but what apparently it looks like there are people who will never really show direct symptoms. But then again, you can discuss what are symptoms here. It's a very subjective thing. So maybe they had very mild symptoms and they just didn't realize. So sometimes it can be hard to say what do we really mean by the onset of the disease by symptoms. But for HUS, this is not a problem because it's very clear. So, and usually only the onset of disease can be observed, not the exposure time. You might have a few cases, we will show that later on, where you know the exact time of exposure because, for example, they were travelers who drove through Germany and more or less spent no time except eating a sandwich at a German gas station, at a gas station in Germany. And then they continued the road trip, and that was the exposure. So you know exactly when the exposure to the disease was, when they eat the sandwich. But for others, they had a 1-2 day stay in the country, and that then you also know something about that. Could, for example, in other context here, time to AIDS, so that was the disease due to HIV infection, so that was the virus. And here, this is the example we mentioned. And for a purpose of this lecture, I will simply assume that this will be a discrete random variable, so not a continuous random variable, but a discrete random variable. And I will say it starts with 0, so 0 days is very unusual but there are diseases where you are immediately having symptoms, like sometimes a norovirus outbreak can be like this. But we will say that it's 102, and that's the number of days after exposure to the disease. And we will characterize it by the probability mass function. So what's the probability that you will have symptom onsets 0 days after infection, 1 day after infection, and so on. That will be our incubation time distribution, and it will be a discrete distribution. And what the back projection does is try to infer the time of exposure of individuals, but when you only have the data about their onset of disease. So here is an example of an theoretical incubation time distribution. We will use that as a motivating example in a simulation-based way, so we can study what's going on. So we will say this will be a log normal distribution with some mean and log on standard deviation on the log scale and so on. And we will typically see that here we will have that the peak seems to be about 6 days. So the median, no, that's the maximum will be about 6 days, and then we have to compute the median and so on. But this will be, for example, a typical model for an incubation time distribution, the log normal distribution, which here I've discretized. So again, remember that I'm doing point source outbreaks here. So I'm doing foodborne outbreaks, and one could be a point source. It's simply available in stores one particular day. So that's, I'll say on day 25, there will be an infections substance which is consumed. So I will say it's such that 55 individuals are exposed to this agent, and I will say in each of these will be the number of infectious encounters with the agent. So of course it could be that there are even more aided ends, but some didn't really were affected by the disease that we cannot rule out. But here will I assume I will just count. It's a simulation study first. I will assume that there are 55 which will get sick, and the onset of disease, so that's when you will see them in, for example, any database, when you report them by symptom onset, is each of them will be randomly drawn realization of this distribution here, which is the number of days until onset, which can be like quite long for some of them. It might be a bit too long for some diseases, but for others you can have such delays, right? So this will be the 55 individuals. This is one realization, so it's not a deterministic thing, it's a stochastic model, right? But this is the realization that I'll be looking at here throughout the lecture. This is how it is scattered. And here it's important to realize no person-person transmission. It's just those 55 individuals all infected at time 25, and it's just you scatter them around by adding for each of them to the number of 25 realization of this, you could say, multinomial distribution between 0 and 50. That's what we added to them, and that's what you will then see in the data. And what we are now interested in, that would be our job as a public health specialist, is try to infer from this graph, maybe knowing something about its foodborne disease that has an incubation time and knows something about how large this incubation time is, that you want to infer the time of exposure, because that's when you need to figure out what did they eat, right? Because at the moment you analyze this data, you might not know what is the source. So you want to try to identify what did they eat on a particular time point. So there will be 25. So when this, when they say I ate at this restaurant on day 25, then you have a good indication that maybe something is wrong at that restaurant. You want to investigate that closer, right? So it's really about trying to identify what they did in time, and not for a really large span of time. But what did they do on a particular time interval? And here it would be one particular time point, right? So just as a second example is, we will say, well, sometimes it's not as easy as a point in time, it's an interval, right? So we start at T0 and it's active for L days. It's in the store, you can buy it in the store. And the question is of when it is bought within that interval. I will say each day is equally likely, right? So it's simply their L plus their L days where it's active. So on each day, the probability that somebody who's got infected bought it on days in these L possible days is 1 over L. So here it's when it's 10 days and there are 200 individuals infected, I get a curve like this. Again, these are just exposures within that interval, and then you add an incubation time on top of that, which is your realization. So how can we infer the time of exposure? So here we would want to, from this curve, infer that they were infected in the interval between 25 and 34 times the days. Okay, so there are a number of sort of heuristics going around, especially also in the epidemiological literature, is, well, try to determine the exposure interval by subtracting the shortest incubation time from the first case and the longest incubation time from the last case of the epidemic curve. So if you do something like that, you get, for the example one, which is here, so YTS is the example one, is that, okay, you would get that they started the one which has the highest number of exposures by this method here. We'll subtract something from the first case, and from the last case, then we get that it's 26, and the length of it is 1, so that's not so bad an estimate. And if we get here, we get 27 and 13 for the one which started at 25 and had a length of 10. So here we're a bit off for that, and of course, in principle, we're also a day off. So, but the problem is that this method is not very good, because it ignores that there is it ignores a bit the structure of the incubation time. Even worse is what you typically see, and is that you subtract the median incubation time from each onset. So you simply shift the curve to the left, either by the 5 days, which I said, or 4 days. So you shift the entire curve to the left, and so here is the median of the distribution, and then you simply say, well, you take the curve, you say that the median of this, I don't remember the exact value of this, somewhere here, and you subtract that from the curve, and then you get the gray curve, which is your exposure interval, and you will realize that this is not very good, because the problem is that this method ignores the order of events in the epidemic curve. Of course, the one which has the first case you see is you subtract the full median of the incubation time, and then you get too far to the left, because the reason for this case being the first one you observe is either because it was the first one which was exposed and had a very short incubation time, right? And this and had a short incubation time is not reflected by taking the median of the distribution, right? So you get too far to the left. So that's why there's a suggestion of using more mathematical models to do this inverse. You want to infer in a convolution, you want to sort of x plus y is z, and what you really want to do after observing z is you want to do, and knowing something about the distribution of y, you want to infer the x, right? So really what you want to do, maybe I'll write that here. See if I can annotate, draw something here. So as I said, what we have is we see what we do is a convolution. So x is the time when really people got exposed, y is the incubation time, and what we will then observe is the time when they really got infected. So we observe z, and we know something about the distribution. So we don't know the exact y, but we know the distribution of y. And what we really want to do is do something and infer about x from all of this. And that's the job which the backpropagation is supposed to do. And that's what we will talk about now. All right, good. And this is a method which was invented as part of the response to HIV and AIDS epidemic in the late 80s, beginning of the 90s. And this is one particular, I'm going to talk about one particular by Niels Becker, a non-parametric method. And we will use the AIDS epidemic as a motivating example for this. So in order to understand the algorithm, it's important to understand what I mean by this delay distribution, or here it is the incubation time distribution. So let's say that N1, N2, N3, N4, N5 is the number of people which got exposed at a particular time point. So N1 is the number of people who got infected by the disease at day 1. Here it's at day 2, or time interval 1, 2. It could also be weeks or quarter of a year. It depends on what resolution you are, but I'm simply going to say day, because usually in these days you would be sort of like anything below a week is standard. So a week or below is standard. Right. So here are the number of individuals that you would have incubation time of 0 days. So you would see them on the same day, N1 not. That is what you will see on the first day. But there will be some which have an incubation time period of 1 day, and of course, happening at day 1 with 1 day of incubation time. That's the ones you will see on day 2 in your report about when they had the onset of the disease, so disease onset. So these will be the end, and those will also be the ones which you will see together with those who got infected by the disease on day 2, but they immediately got the symptom onset or within the first day. So altogether on the same day. So these two you will see as having their symptom onset on day 2. These you will see as they're having their symptom onset on day 3. These you will see as having their onset of symptoms on day 4, and these you will see as onset of day 5. So this is what this equation says here. It's the number of incident cases in interval t. That's the ones you're going to be seeing as having disease onset on particular time t. Is you always do these diagonal sums here in this delay matrix. Let's call it that for the purposes of this. And as we said, sort of like I assume that I know this and that how they scatter. But if you only have these, then you can compute the nt. So as a function of time by simply adding up row wise, right? That's all these added up, they will be n1, all these added up will be n2, and so on. So these are the nt's are what we're interested in, and what we will have observed is the y of t, right? And please note that we use the t here because there's a time dependence on all of this. And this will be reflected in this model. So what we will assume is that nt is a Poisson distributed random variable. So you might need to look up Poisson distribution, but we already used that previously in the lecture. And it's simply a count data distribution. And if nt is distributed like that, then we know that since we always observe a particular fraction, how many will have their symptom onset at day 0 will be defined by the probability mass function of this incubation time period, and that will be, for example, then f naught times lambda of t of those who have it on the same day. So nt naught will be f naught times a lambda of t, and it will be Poisson distributed random variable, right? And if you do these equations, then you say y of t is going to be given like this, and if you sum up independent Poisson random variables, then you can simply also sum up the expectations to get the expectation of the sum. And this is what this equation then here, you will see that the mean number of cases, so that's mu t, so e of yt. Hang on, I can again do annotation and draw like this. So what we're interested in here is the e of yt, and that's what will be mu of t because we assume that it's Poisson distributed. So this is the characterization of its mean. And you know always that you can compute the mean of the sum by taking the mean of the individual terms of the sum and the mean of the individual terms of the sum. So what was this one here, and we know that it is equal to this from up here. So this is what goes in here. So this will be our expected number of cases as a function of this lambda of I, and lambda of t is now our hidden function describing the mean of the development in the expectation or mean of the nt. So this would be sort of the true number of cases, but we say there's an underlying trend. So actually we are interested in the lambda of t instead of the nt directly, because I mean it doesn't help us much to observe these directly. We'll say it's the lambda of t, it's the trend. So of course lambda of t, they are connected somehow. Usually they have a bit of a smooth structure. All right. Good. So let's continue. To clear and continue like this. Right. So what we will be doing, and this is for this example one, is we have here our NTs or lambda of t's. So I'll simply put them at the expectation. So it's the lambda of t actually I'm showing here. And for each of them, I will, so for this green one, which is the number of individuals who on day 25 had their symptoms, I then divide these, here it will be 19 individual. I divide them according to the incubation time period. So this is this here on when these 25 individuals would have their symptom onset, right? So these, I scatter around this. So this is decomposition of the mean based on these who were infectious at day 25. Then are those who, sorry, not infectious, who were infected by the disease on day 25. Then I have the yellow ones are those who are infected at day 26. So that's the next. I add another incubation distribution on top of that. So I always add these according to how large that number will be, as indicated by the circle. And then I add all of these on top of each other. And then if I do a marginal count for a particular time point, that's the number of cases I will expect to have on a given day. And as shown with the cross, that's the observed YT. So the trick is now to choose these values, which, because I haven't seen that, I don't know them, I have to choose those values in order to have these expected number of cases as close as possible to the actual observed data, given that I know the incubation time distribution, because I distribute that every time. If you want to see how this works, I made a small animation, and for that I have to change my share to our studio, which I've done here. So this is the graph that you just saw in the on the slide. And what I'm going to do is I'm going to start with the 25 one. So this one here, I will vary it from here to here, just so you can see what effect this has on the curve, because that's what we're doing for all these time points here, 25, 26, 27, 28, and so on. We're going to, and here we're going to just take 25 to 28. We're going to see which of the values here in combination with the others. I'm just going to here change one by the time, just so for the illustrative purposes, which configuration of these ones here gives me the best fit between the data that I observed and what I would expect from this forward-looking model once I assume the NT. So just to sort of look at that. So here I take at time 25, I try each possible value, and you see the larger the value is, the larger this part becomes, which is due to cases by day 25. And then I change now to 26. And you see, always put out one incubation time distribution on each of these time points. I leave the others constant because that's what I do. And the job is now to sort of fix all these circles here, try to balance them. So the curve that I get here, the mean expected number of cases, is as close as possible to the actual observed value. So that would be my inference purpose. So you can see that's a maximum likelihood issue. And there's an algorithm also for do that, because once you so this can be a quite difficult likelihood because there are as many parameters as you have data points. So this can sometimes be a bit disturbing if you want to really do likelihood inference for all of this. So you add a bit of smoothing as well to make it a bit, say these values are a bit connected between each other. And then the other thing is that you also can do an EM type of algorithm. EMs means expectation maximization type algorithm, so that you say, once I know these, then everything is easy to calculate. And what I always do is first I will try to find these, then given that I will do a maximum likelihood estimator, which is very easy in this case, and then I use that to again update how these values should be. But that goes beyond what is the scope of this course. You just need to know that want to do this in an algorithmic way. And you can think of these sort of like that there's a handle for each of them you can pull up or down, and you want to sort of like find the optimal configuration describing your actual data. They won't fit perfectly because there are stochastics involved, but how can you do it? So again, when I say move up and down, so it's just going on like this, and let's see here. So I can move each of them here up and down, and it will have, as you saw, sort of like sometimes then the curve will go higher or it will go lower depending on how. And what I really want to match is sort of like the curve as it manifested in these crosses. That's what I really want to match. So just to make it clearer, maybe from a drawing. Okay, so that's the plan, and there's an algorithm for that, which I will, because it goes beyond the scope of how much we can expect to know here in the course. For those interested, you can find the details in the slides or in the reference, which we'll be sharing. So I just need to again move to the lecture slides, which should be here, right? So I'm sharing again. Very good. Okay, so back projection is the inverse problem of deducing the lambda t's given the observed yt's. And you can say, okay, what you need for this is an incubation time estimate. And here I just use this log normal distribution. And then it's just to show you there's a function in a 1R package, which is called surveillance, which we worked on for quite a while. And for that, if you take an object which contains the time series, so this was here simply the observed data from this example 1 outbreak, you give it a certain incubation time period distribution in discrete form. Sorry. Then you get, from these observed time series, you get an estimate here. This is the estimator for lambda of t that you show here, based on this back projection. So you see, it actually managed to quite well to try to reconstruct when were those individuals actually exposed. Here there's maybe sort of like an extra thing. There's a smoothing parameter k, which says how smooth should the curve be, and this is a very heuristic argument. You could say it's not something you really for this algorithm try to do by inference, but you could, of course, or should, of course, and that would be maybe the preferable solution, that you try to estimate that. So here we say, I know this is a point source outbreak. I'm not going to expect any smoothing, so I'm going to put that to not. And then it looks like this, which is a nice way to say, okay, I had these data, I knew and it's a bit cheating, I knew the right incubation time distribution. That's not always going to be the case. Then I can get a good reconstruction that actually most of them got infected on day 25. Right? If I used a bigger smoothing parameter, of course, then it's still sort of scattered around the 25, but it's sort of like a bit further out because of the smoothing part. For if you have example 2, where you had this period, then I can also assume some smoothing. You see, you hit the interval more or less, but I mean, due to the smoothing, of course, it doesn't find it directly, but this is a bit harder, of course, also to find in the point outbreak. But you get it, you see that the failure is to take this here as the time of exposure or time of infection of the individual. What really happened is they were infected a few days earlier here, again, to my assumed probability mass distribution, right? So one thing which is at least important to keep in mind for statisticians, so here I showed you the point estimates, but of course there's uncertainty involved. And the method which I describe here, this non-parametric back projection using an EM algorithm, doesn't provide any measures of uncertainty for the estimate directly. So there are two sources which are important to realize. One is the sampling variation in the YT. So we assumed it's Poisson distributed, and that means there's some uncertainty in a variation in the observed data, and you want to sort of, that has consequences also for your estimate of the lambda of t. But of course, there will also be other sources of uncertainty. I mean, first is the Poisson distributed model at all a good assumption? Could be that the variation or the variability in the observed values is larger than the Poisson distribution reflects. One thing to think about. And the other is, of course, we here so far have assumed a certain incubation time distribution, but it's not necessarily that we know this in advance. So this is something we need to sometimes, or often we need to estimate this from data. And of course, that's usually done by a smaller sample, so something which can change over time. So there's, of course, also estimation uncertainty in the incubation time period. Just to sort of show this for how we did this during the STEC outbreak. So in order to try to figure out what's the incubation time distribution, we got cluster data from 91 cases with a well-known exposure time, which typically was an interval. So that would be foreign cases or a cluster. So we have here for each individual is one line in this graph here. There are 91 cases altogether. And this would be, for example, then what was the days they were in Germany, as an example. So there were, for example, travelers from Sweden. I'm not sure it was if they were travelers from Sweden in a group. They stayed in Germany for 2 days, and then they got sick a number of days after. But that's the days which are now entering the incubation time period, estimation period. Sorry, the incubation time estimation is not just a single day, but it's an interval. So it's not you have interval sensor data, and you need maybe to take this to account, or simply take the midpoint. I mean, that depends. The clean solution is to take interval sensor data, because you just know that it was within that day. You don't know exactly when it was in the day, but here it's even 2 days, so you might want to take that into account. But the sort of the quick and dirty solution is simply to take either endpoint or the middle of the interval, and then ignore that that you don't really know that within the given day. And then you can get an estimate. They're interval censored data estimator, and here's a method called the Turnbull method, which is something which you would learn about in survival analysis if you are interested in such courses at the statistics department, or at the mathematical statistics lectures. I think the statistics department also has that, and the mathematical statistics also has a master course about this in the fall. And that's the estimate you would get here if you use a non-parametric estimate and with some uncertainty intervals around that. And then if you combine that incubation time period, and there's also some dependence on age, even so, you really do a survival model, but you don't need to know how you do that. But that's the important part, is that if you do these backpropagations, then you would see sort of like the estimated time of exposure in cases of when they got infected. For the HUS cases is somewhere lying around here, which is way earlier, of course, than the peak in the symptom onset. So there's a bigger delay between these two here. Maybe it's 18th, 19th of May is when you observe the peak. And it would be here 9, 10, 11, 12, 13 of May when actually the peak in exposure was. So remember, that's when the Robert Koch Institute heard the first time about the outbreak, was on the 19th of May. And at least for the HUS, that's when already the number of, it was already starting to go down, right? The warning was about eating cucumber salad and tomatoes or associated products in northern Germany. It was on the 25th of May, and in some sense you could say the outbreak was almost already over when this warning was given. So the question is how beneficial it was. But please remember, when you have to assess something like this, how the data situation was at the time point of May 25. It's easy to say something smart in hindsight, but you always also have to remember how the situation is. So that makes it more difficult. But of course, also you want to have sort of this prevention strategy that you might want to affect certain behavior in individuals. So it's sort of how to formulate a proper public health warning. That's an art and a science of itself, but it's not for mathematicians to be majoring in that. But as mathematicians, you need to know something about that as well, of course. So that was you can use the back projection to say something about when was the time of exposure, and that's often the very relevant thing, because that's, if somebody got disease, for example, for COVID, at least it has to have happened at some point. Whether they show symptoms or not, that's the next problem. But this is which all cases have in common, that they must have been infected by the disease at some point in time. So that is also a way to adjust for that. Okay, just a few maybe discussion points. So it's a non-parametric method, so there's no underlying assumption about the mode of transmission. So you can use this for person-to-person transmitted diseases just as well, point source and so on. There's no SIR model lying behind of this. I've seen some works for people doing sort of like also what is related to a back projection using an SIR model. So they say there's the exposure and something, and then you see at a later stage you observe something in these individuals, but then you have to really make sure that your assumptions about the model is right, and the SIR model, for example, for the foodborne based outbreaks, are simply wrong. So that's the beauty of this method, is that you don't really need to know a lot about the mode of transmission in order to be able to sort of try to reconstruct the curve of infection in individuals who at a later stage show symptoms. Okay, but of course, this also suffers from bias. If you have a large underreporting of cases, then of course this also suffers because you don't get the cases. You only would extrapolate or back project those cases that you actually observed. And then you need to be aware that if you go very close to where you have actually data, then you would know that some cases are missing, and you might need to be able to adjust for that. So that actually that speaks for that you might need to combine with the second method, which I will talk to after in the second part of the version of the lecture. And if you're interested in some further reading on back projection, look at some R code and so on. There's a good paper by Egan and Hall from 2015, which might be also something which you want to work on in a project for the second project. Right. So with that, I'm gonna stop the recording for now, and I'll be back with part B, one link click later. Okay, thank you.